So maybe I can. No, like this?
Maybe
Yeah. Frederick. Okay, so meanwhile, I'll introduce our next speaker. So it is my pleasure to introduce Dr. Peter Boorman, who's currently a postdoctoral scholar at Caltech. Peter obtained his PhD in astrophysics at the University of Southampton in the UK in 2019 before becoming a postdoctoral researcher at the Astronomical Institute of the Czech Academy of Sciences in Prague in Czechia. His research focuses on understanding the structure and evolution of the environment surrounding growing massive black holes and how this region connects to the surrounding galaxy. Peter also has a keen interest in astrostatistics and methods for exploring astrophysical data, including parameter exploration and data visualization. So as Elena mentioned, Peter has been using VXA for a number of years. Peter is also a member of the UVEX collaboration for the Ultraviolet Explorer. I think it stands for Ultraviolet Explorer. Please correct me if I'm wrong. And many people involved in this collaboration are based in Caltech, and it is expected to launch in 2030. And today, Peter will be talking about unveiling the missing sites of massive black hole growth. So Peter, thank you for accepting our invitation, and take it away.
Peter, you need to unmute yourself.
Oh, yeah. Sorry, you're muted, Peter.
Can you hear me now?
Yes.
Yeah.
Yes.
Perfect. Yes, thank you. So yeah, thank you for the lovely introduction. And yeah, it's great to be here to talk to all of you today. Sorry I can't be there in person. But as Julia mentioned, so today I'm going to be talking about some work that I've been doing, all about the obscuration surrounding growing massive black holes. Okay, so let's get into it. Oops. There we go. So in terms of a base level motivation, I always like to start with the X-ray background, right? So this is the integrated flux of light in X-ray energies at every direction on the sky if you were to remove point sources. But the issue is that you can't remove point sources from the X-ray background, because even the ones that you don't resolve, the X-ray background is comprised entirely of the integrated X-ray emission from point sources. So here on the left, I'm showing the deepest X-ray observation of the X-ray background taken to date, where you can see that with Chandra, with 7 megaseconds in Chandra Deep Field South, you really start to pick out these point sources of X-ray lights, where the vast majority, if not all of these, are AGM, so growing supermassive black holes. Now, if you were to translate this information into another form, so as a spectrum, which I'm showing on the right, which encompasses every growing supermassive black hole across cosmic time, the general shape is that it's a very broad radiation ranging from 1 to a few hundred keV, but also that it peaks at around 30 keV, and that'll be important a little bit later on. So that was every growing supermassive black hole. So I just thought I'd start out by painting this approximate picture of what a single supermassive black hole, the different components that I'm going to be talking about today. So here I've just set up these axes in parsec. And if you were to consider a 10 to the 8 solar mass black hole, then the Schwarzschild radius of that black hole is approximately shown at the center here. I hope you can see my cursor, by the way, but yeah, please tell me if you can't. Then just arbitrarily, I've also marked out at around 100 parsec this region of circumnuclear space within the galaxy. This is completely arbitrary, but it'll be there it'll become apparent why I've put it there in a few slides' time. And then, broadly speaking, you have a host galaxy encompassing everything. Now, if you have enough material that wanders close enough to the black hole, you get an accretion disk, and that's the primary source of the radiation in AGM arising in the optical and the UV. But then, because of this X-ray corona, where you have a hot gas of electrons, you get your primary emission in X-rays from Compton upscattering of those optical and UV photons into the X-ray regime, right? And this is your primary radiation that comes from AGN in X-rays. But there is another component that I think is often overlooked, which is this gas and dust obscura. Now, this is broadly speaking, the region that talks between the host galaxy and the AGN circumnuclear region, which is the reason I put it at a roughly 100 parsec in this cartoon. But it's essentially the middle ground in terms of the way that the host galaxy can talk to the black hole. So it's incredibly important. And as I'll show later, studies do suggest that this should be prevalent in essentially every AGN, where the level of obscuration to some extent is dominated by your orientation towards the circumnuclear region. So in terms of quantifying the level of obscuration along the line of sight, in X-rays, you tend to use equivalent hydrogen column densities. So here I'm just showing two obscurations with the proviso that anything greater than roughly 10 to the 22 hydrogen particles per centimeter squared is broadly dubbed as obscured, right? So that's the general classification that gets used. But just in terms of analogies, the very approximate column density of two sheets of paper is also corresponds to roughly an NH of 10 to the 22. And then if you were to take that analogy even further, roughly 10 to the 23 is the column density through a human hand, right? So just to put it into perspective. And now the X-ray spectra that I'm going to be talking about today are actually relatively simple because they can be simplified down to essentially considering two components, right? So you have your direct transmitted component, which is in blue. This is just the emission coming from the corona that I showed just now that can get through the obscuration, and this gets absorbed by photoelectric absorption primarily. Then you have the reprocessed spectrum, which I'm showing in red, which is broadly speaking fluorescence lines and an underlying Compton scattered continuum, where the strongest fluorescence line, as many people will know, is iron at around 6.4 keV. But when you start to get more and more obscured, so above the Compton thick limit, essentially the inverse of the Thomson cross section, which is roughly at 10 to the 24 per centimeter squared, but it does depend on things like abundances. You get a spectrum that starts to have more and more of a contribution from the reprocessed spectrum until eventually you get to 10 to the 25 or thereabouts in column density, at which point the transmitted spectrum can't be detected at all, and you're dominated by this reprocessing, as you can see in this right-hand plot. And just to continue this analogy, for 10 to the 24, it's approximately like trying to look at the sun through a rain cloud, and then for 10 to the 25, it's more like trying to look at the sun through a thundercloud, right? Not a lot gets through. So why am I telling you this? Why is this important? Well, studies of population synthesis that aim to try and reproduce populations of AGN across cosmic time as a function of their redshift, column density, and luminosity, they tend to always find or predict that roughly 30 to 50% of all AGN should be Compton thick at any different redshift, right? And whether that evolves is still an open question, but it could be even higher, essentially. So on the left, I'm showing again, the same plot as I showed before, the observed X-ray background spectrum. And then on the right, I'm showing the population synthesis models of Tanima Anana et al. In 2019, where you can see that if you try to reproduce this spectrum with just unobscured AGN, there's a very relatively small contribution. If you include obscured stuff, so sort of two sheets of paper or more up to the Compton thick limit with this purple dashed line, it still can't reproduce the peak. But the general shape of the cosmic X-ray background can only be reproduced if you include these Compton thick AGN. And I'll just say that even though this difference between the obscured and the Compton thick inclusion may not look like a huge amount, because Compton thick AGN are so obscured, to be able to get an observed amount of flux of this increase, you actually need a huge amount of Compton thick AGN, which is the reason that you expect these huge populations of like 30 to 50%. But this is across all cosmic time, right, with population synthesis. And this is a prediction, right? And so it does bode the question of what would you expect in the really, really local universe where constraints should be optimized. So in terms of a local universe, I thought I'd just arbitrarily choose or define this region, so roughly 200 or so megaparsec. And just for reference, I've just plotted 3 well-known sources on here, so M87, the Coma cluster, and our closest quasar, Markarian 231. So essentially this volume is kind of up to the boundary of when we start to detect quasars, right? So this is the local universe. And then if we were to create a y-axis on this plot, which is the Compton-Thick abundance of the population as a function of this distance, what I was just saying, so the predicted Compton-Thick AGN abundance should be at least 30 to 50% if you don't expect significant evolution in this very small volume, right? But the current constraints that we have from hard X-ray flux limited selection, so i.e. just trying to select Compton-Thick AGN purely from their observed hard X-ray flux, it really struggles to find these sources, right? So here I'm showing the dedicated new star follow-up of SwiftBat selected Compton-Thick AGN, analyzed by Nuria Torres-Alba and collaborators in 2021. There have also been a number of other studies that have found similar trends, but you can see that even within 40 megaparsec, so really, really nearby, you still don't get the predicted fraction of Compton-Thick AGN that you would expect from these population synthesis models. So it is a bit tricky. But taking this one step further, last year I created a sample or a database called the Database of Compton-Thick AGN, or DOCTA. And this sample was designed to be literature complete and quite lenient with the definition of Compton-Thick in the literature. So what this contains is every AGN that's been analyzed with new star data to get a good constraint on the Compton scattered continuum, but for which at least one reference previously has found it to be Compton thick. And when you do that, there is only 66, right? This isn't an inset from this population. This is all of them. And I've ordered these by signal to noise. So the brighter objects are at the top, the fainter ones are at the bottom. And each panel contains the residuals you get when you fit a power law to the observed spectrum. So that's why just to accentuate the iron line and the Compton hump in each source. And also, I would say that the variability does seem to be quite common in the ones that have been observed multiple times. So those are the ones with colored points in their boxes. But you can see that the vast majority haven't been observed more than once. And those are the ones that are colored in white. So this is still a very open question. And this population is still one of, if not the most elusive AGN population there is. So to try and tackle this problem, we created a sample called NewLands. So this stands for the New Star Local AGN NH Distribution Survey. And this is a new star survey of mid to far infrared selected AGN. Now, the selection was by design, very simple. It started with IRAS and just selected to have sources that were detected at 25 and 60 micron in the point source catalog. Then based on the gradient of the 25 to 60 micron SED, you can select sources that have an SED in mid to far infrared wavelengths peaking at hotter temperatures, which tend to be indicative of AGN, than non-AGN, which peak at cooler temperatures at longer wavelengths. And then just because we wanted a succinct bona fide AGN sample, we just relied on optical spectroscopy to really get bona fide AGN. So to get type 1s, 2s, and then the non-AGN according to their optical lines. Whoops. And this confirmed 122 AGN in this sample. Now, the whole idea behind this selection is that we were trying to be representative of the population. We didn't want to be complete. We just wanted to select a carefully selected sample that is deliberately biased, but biased to the unobscured and the obscured AGN with approximately an equal way, right? So here in this similar schematic as earlier, I'm showing the circumnuclear region with this obscura where the mid to far infrared continuum could be arising from. Of course, it could also be coming from the host galaxy itself. And the same goes for the narrow line region, right, which emits this O3 line, which is one of the most powerful indicators of the narrow line region in the optical. And that can come from the host galaxy as well, or it can come from the narrow line region, right? And so for all of these sources, if you have what's called an isotropic sample, or a sample that should select unobscured and obscured things roughly equally well, you would expect the optically obscured things to have the same narrow line region to mid to far infrared continuum flux ratio as the obscured type 2 objects, right? And so I'm showing these two flux ratios where I'm choosing different mid-infrared fluxes on the left and right here, where you can see that the red points, the type 2s, are almost identical to the type 1s. And you would not expect this if you were preferentially selecting brighter type 1 objects, or if you were preferentially selecting dusty type 2 objects, right? So this is why we're quite excited about this sample. But I did mention that this is a new star survey. So what does new star bring to the table? Well, I really like to show this plot, even though these two sources aren't actually selected from new lands. These are just two AGN that I'm currently writing a paper on that were selected in a slightly different way. But these are very local AGN that were selected to be powerful Compton-thick AGN. But if you plot their archival soft X-ray spectrum, it peaks at around 1 keV, which is indicative of just a non-AGN system where you see thermal emission arising from the host galaxy. But if you observe it with new star, that's when you start to see these features like this ion line and this Compton hump that really can't be picked out on average for serendipitous sources that have only been observed in soft X-rays. And just to note that this source on the right does appear to be an entirely new type of Compton-thick AGN with an intrinsically steep spectrum. So please do, ask me questions or reach out if you're interested about that. So the ultimate result from this survey is that 35 plus or minus 9% of those AGN in new lands were found to be Compton-thick. That plus or minus 9% is very important here because we were very careful to include the uncertainties induced by using different models. We used in total around 23 different models, or around 10 models for the obscured sources in this sort of pie chart, this oversimplified NH distribution that I'm showing here. And so the uncertainties here may seem large to some of you, but those uncertainties do include the extra degeneracies that you get by choosing a model, which can become very important when you have Compton-thick AGN. We also find these proportions of obscured and unobscured objects roughly in equal proportions. And I would also note that we don't over select or actually select many ULERGs or LERGs at all, which are often found to be Compton-thick obscured, which does suggest that maybe this 35 plus or minus 9% is still a lower limit. But the fact that we find these flux ratios that suggest the sample is isotropic, it does point to that not being the case. So it may suggest that this NH distribution is more valid for the circumnuclear region, as opposed to ULERGs and LERGs, which tend to have very dense obscuration, but on host galaxy scales. So if we go back to this plot I was showing earlier with the hard X-ray flux limited selection from SwiftBat, I'm showing this decreasing trend below the predicted Compton-thick AGN abundance. With new lands, we of course have larger error bars because we have far fewer sources, but the fraction for the whole sample, 35 plus or minus 9, is fully consistent with this range. And then if you actually bin it up into 3 bins in distance, there may be a systematic trend of decreasing, but within uncertainties, they are all fully consistent, kind of showing that we can select these Compton-thick objects with mid to far infrared selection pretty well, going out to our within distances still within our local universe, which I think shows some prospects for using Prima in the mid to far infrared in the future to select more of these objects at lower luminosities. But if I plot this up into what I like to call the Newlands AGN iceberg, so what this shows is every X-ray photon in every X-ray spectrum that I used to analyze the AGN in Newlands If you plot them every single source stacked by their observed signal to noise, so brighter objects are at the top and fainter objects are at the bottom, this is what you get. Now, I also went and colored the optical type 1s in blue, and then I colored the optical type 2s, so the obscured objects in the optical, with a sort of red-yellow color bar, right? And you can see that already the brighter objects almost always tend to be unobscured or lower obscuration, right? But it's not until you get to these lower observed fluxes that you really start to pick out the not just type 2 obscured objects, but also the ones with the Compton humps and the strong ion lines indicative of being a Compton thick AGN. But the fact that in the lowest rows here seem to be extremely faint even for new star, it does hold some prospects for a concept like the high energy X-ray probe, essentially a more sensitive mission in hard X-rays in the future would be very powerful for trying to study and understand these objects down to a flux level that could essentially select everything above, say, 10 to the 42 in X-rays. So that was everything I had about new lands, but just in the last few slides, I just wanted to talk about a slightly analogous project that I did last year, all about intermediate mass black holes. So just to sort of paint a very broad picture, we know of dense obscuration in stellar mass systems, things like GRS 1915, for example, and SS 433. And as I've been talking about, we know of Compton thick and heavily obscured objects for supermassive or growing supermassive black holes, also including U-lurgs and lurgs and compact obscured nuclei. But previously, there has been a big difficulty in trying to find intermediate mass black holes or intermediate mass AGN that are also Compton thick, right? That was until IC 750. So this object is the second closest intermediate mass AGN to us, behind NGC 4395. And it has a black hole mass measurement from Inginzor in 2021, placing it at around 70,000 solar masses, but within uncertainties below roughly 100,000 or around 100,000 solar masses. So this measurement is from a water megamaser, which tends to be one of the most accurate mass measurements for AGN, and placing it firmly in the intermediate mass regime. But it wasn't until it was observed with a very, very deep Chandra observation that it was found to have a very bright or seemingly bright point source at the center, as well as many off-nuclear point sources in the host galaxy that you can see here in this image from Chandra. This is around 177 kiloseconds of data, so a very long exposure or net exposure. But if you take that point source, you get the white spectrum here showing a very strong ion line, very indicative of what I was showing earlier for Compton thick AGN. And also we had a recent, this cycle, new star observation of around 220 kiloseconds, so also extremely long, to try and constrain the broadband X-ray shape, including the Compton hump in this source. And you can see that based on the new star spectra that are co-added in this plot, you can see that it has a general shape that's entirely the same as the previous plots I was showing of Compton thick AGN. And it is somewhat confusing me at the moment as to why an intermediate mass black hole would have such a similar broadband X-ray spectrum as a supermassive black hole or a Compton thick supermassive black hole. And given the general pattern you see here of having to resolve these comparably bright off-nuclear sources, I think this really shows some strong prospects with Axis in the future as well. So that was everything I was going to talk about today. So just in terms of some take-home points, firstly, there is a huge amount of AGN that are currently missed in our nearest cosmological volumes, and this problem is going to be even more extreme, if not just as bad, at higher redshift. With new lands, we selected unobscured and obscured AGN with approximately equal efficacy, finding that at least 35 plus or minus 9% should be Compton thick. And then in terms of intermediate mass black holes, the broadband X-ray properties we constrained for IC750 kind of suggest that these obscuration biases are probably similar for the intermediate mass AGM population as well. So with that, I'll just finish and thank you for your time.
Thanks a lot, Peter. We have time for one quick question.
First, I'll ask about the intermediate mass black holes. Your conclusion about the IMV population is based on one object that we know of. But what do you think as perspectives, perhaps for future surveys, to find more stuff like IC750?
Yeah, that's a great question. So indeed, it's only one source. I would mention that the Compton thick fraction within 5 megaparsec for supermassive black holes, based on just 3 sources, is fully consistent with 50% of being Compton thick, right? So it kind of suggests that maybe within these local volumes, it can be useful. But yeah, I completely agree. You need more. In terms of future surveys, I think Axis is kind of the optimal to try and constrain these things if you can detect enough photons in the ion line, essentially. Because with the Chandra spectral fitting of IC750, without a sensitive enough detection of the ion line, the spectral fitting can become very degenerate between unobscured and obscured solutions. Yeah.
Okay, thank you, Peter. Let's thank Elena and Peter again. As a reminder, there's